coming. And okay, let's start the afternoon session. Our first speaker is Dr. Velasco, and she will tell us about tracking down the route to the standard model with inflation and gravitational waves. So are you
Hi.
ready?
Yes,
Yeah,
I'm ready.
please start. Yeah.
Thank you. Yes, thank you for accepting my contribution. I will now turn off my video and I will restart it at the end of the talk. Thank you.
Okay.
So the title has been said. So this is a work in collaboration with Professor Chun at the Korea Institute for Advanced Study, where I am spending some time, very nice time here. And the outline of this talk, of course, is brief because we don't have much time. So I will present the motivation and then see if it's possible to discern among SO10 models based on their predictions of gravitational wave signatures. And then I conclude with a summary and outlook, maybe hoping for computational improvements, of course, both from the theoretical side and from the side of the people making the simulations with regarding cosmic strings and phase order first transitions. So the motivation is that, as we know, that unfortunately, LHC will not discern many low energy signatures of grand unified models. But instead, we have the great opportunity of using gravitational wave experiments to discern among many models. So this is the main motivation. As we all know, grand unified theories have a lot of predictions, and the most famous, as you may recall, are gauge coupling unification, proton decay, but also, and this is something that has been the focus of intense research in the last 3 years, topological defects such as monopoles, cosmic strings, and domain walls. So for a very long time, these defects have been seen mainly as a problem. But now are they seen as an opportunity because we may be able to be lucky enough to detect some of them, and then we can compare to the predictions of the grand unified theories. So the one important question is that, is it true that can we distinguish among models? Because we know there are many uncertainties, many model building, fine tuning. So this is the spirit of the work and the talk. So this just to, as a quick remember of topological defects, this is a very nice image from which we can understand what a topological defect means. For example, if we compare the sphere and the torus, we know that the surface of the sphere is connected. So you can go from one point to the other in a smooth way. But you cannot go from one point to the other in a trivial way in the torus. And actually, you can see the torus as a quotient of two groups, R squared over Z squared. And this gives you another group, Z squared. This is called the homotopy group. And if these kind of quotients are not zero, then we say we have a topological defect. So the main idea then of the topological defects are they measure some discontinuity in our spaces. And that's why when it was realized that grand unified theories possessed these features, they came as an unwanted surprise. But let's see how can we make physics out of it. So there has been for some time now a work, this is a work from 2003, This is a quasi-complete classification of God models according to their topological defects. So it's a quasi-complete because it left out some models that at the time it was not possible to achieve due to the complication of proton decay. But nevertheless, it is, the most powerful attempt of the classification of models according their topological defects. Sorry. So following their notation, where 1 stands for monopoles, 2 for cosmic strings, and 3 for domain walls. This is a diagram from this paper in which you can see, for example, if you want to follow the esotherm route and you want to break to the 5, the SU5, times 1U1, vector U1. So this is this route will create at the first step monopoles. Then at the second step, when you are left with a Z2 symmetry, will create cosmic strings. And then when you go down to the standard model, it will create again monopoles. So of course, if you want to realize this model in nature, this scale has to be very large, and it needs to happen before inflation. And it is in this way that one can make sense out of all these chains, possible breaking chains. So in this talk, I will concentrate rather on the chains that are produced not on given the SU5 models, but on given either the Patti-Salam or this group, the standard model group, times B minus L. So you see maybe why, because it offers much more model building, and it has these models have been explored in the past. And for example, we can take an example. If you want to break directly to the Patti-Salam, so SU4 color times SU2 left times SU2 right, in the first breaking step, you will have some monopoles. And then if you go in this path, this represents this blue rectangle, you will go, you will have many possible routes. Again, producing monopoles, you break the SU4 of color, giving rise to SU3 and U1 B minus L, and so on. So you see why it's nice to follow this kind of change, because it allows for a lot of model building. So more in detail, this is a sample of models studied in the literature. And I said models studied in the literature because they have been studied from all points of view: proton decay, Gershon amplification, matter spectra, phenomenology, which are relevant to the LHC, which unfortunately is not longer the case, but still most of them survive. But surprisingly, from this list, for example, only 2 of them have been studied from the point of view of their topological defect signatures. And these are the ones by Lazaride, Shafi mainly, because these 2 authors are in both of them. And this was actually the groundbreaking article in which topological defects were studied, not for the first time, but in a way that it was understood that it could be not seen as a problem, but as a benefit, because gravitational waves could be produced. But these others are well motivated and satisfy all constraints, but there hasn't been the motivation to study from the point of view of topological defects. So in this talk, I will choose this one mainly, which has not been studied, and briefly compare it to this one. Because, and why? Because they have very different signatures. And the point of this talk is to exemplify how these signatures can make us realize which model is the most favored model if we are lucky enough to see gravitational waves. So I start with this one. I will explain this. So this is based on a model in this review article in which the construction of inflation is based on Starobinsky-like inflation. And this has very nice features. The main feature is that, well, it is broken by some Higgses of desert 10, 210, a pair of 126, down to not the Patisalan, but directly to SU3 color, SU2 left, U1 right, U1 B minus L. Then a subsequent breaking happens at and this has to be more or less the same scale. That's why I put God in the same with the same name. It could be a little bit lower, but it doesn't allow to be more than 2 orders of magnitude lower to the standard model, and then subsequently at the electroweak scale with the template. So in this model, so you have monopoles, then you have cosmic strings. So what you want is actually to have this inflation at 10 to the 13 GeVs. And at the end of inflation, this you break V minus L. And then you go, this is a very high scale still, and you wait a lot for this electroweak symmetry breaking. So this is basically the main picture that you can take. This looks like this. So this is a typical way of representing the signals in a plane, the frequency of the gravitational wave times the density. So we know that there is a bound here, which is okay. And then there is a plethora of experiments now, fortunately. So this is nanograph. This is SKA, LISA. These dotted lines means that these are projected experiments. So LISA is projected, the SIGO is projected, BBO is projected. LIGO has already given some, of course, bounds, which are currently about here, but this line is a projector subsequent run of LIGO. So in this model, these cosmic strings will appear between these scales, 10 to the 13 and 10 to the 12. So it's in this, within this band that we expect to see. So you see nanograph has not seen this. SKA can see that. LISA can also see that. And also, well, unfortunately, it's difficult to build in these models phase order phase transition. Is typically the kind of phase transitions that are in God theories are second order phase transitions. But it's not excluded that in some parameter space that could be first order phase transitions. But this will happen in any case at a scale 10 to the 13. And you know, a curve of a phase order phase transition happening at 10 to the 13 GeV will have this profile, which will be missed completely by these experiments. There is, however, a variation of this following this work. And this will allow, is basically the same model, but you follow a kind of trick, and now with chaotic inflation, instead of B minus L left completely broken at this high scale, you can allow for the possibility for restoration of B minus L and subsequent breaking close to the electroweak scale. And then, of course, this can give you a phase transition lower than 10 to the 13. So this is again the same, basically the same plot as before. But now, instead of a phase order phase transition at 10 to the 13, you will have a phase order phase transition at 10 to the 8 GBs. And this one could be catched by LIGO and the SIGO and BBO. So there you will have a way to discern among these models. So I think I better go to this since my time is off. And because I want to make the comparison to the works by Shafi and et al. So they have chosen different approaches to inflation. In particular, hybrid inflation works better with this kind of scenarios. They have two scales of breaking, but inflation actually happens before the production of cosmic strings. And this is quite different from the case that I presented before, rather the cases. Rather to see one cosmic string expanding along LISA and LIGO possibly, you will have the profile decaying here. But still, it could be catched by LISA, the SIGO, BBO, and it is claimed that it may have seen by nanograph, but missed by other experiments. So to summarize, what we are proposing in this work is that rather to do than to do a general analysis of models and where some cosmic strings can happen or not, we focus on models that have been developed and satisfy phenomenological constraints. And we ask the possibility if it could be possible to discern from each other. And just to give you an example, the theoretical calculations, from the theoretical calculations, and I mean just our model building, in terms of, for example, how well you can calculate the scale of the string. Cosmic string uncertainty, just the model building, it has 30% because we don't know exactly this scale. And the main parameters of phase order phase transitions, which I have no time to describe, but these are two of the most important parameters, have this uncertainty, 15% and 10%, depending on the model. So these are the two first models that I present. So obviously the message is the following. It is possible and it is exciting, but we need to do a lot of effort from the model building point of view in order to bring down the uncertainty and to say the scale at which, for example, the string happens, or the scale or these parameters, for example, in order just to reduce the theoretical uncertainties. Another thing, of course, is that how well are done the simulations, because also they carry a lot of uncertainties, and therefore it's difficult to really come out with something very specific. So thank you for your attention.
All right, thank you for the talk. It's time for questions. Any questions? So we are a few minutes behind, so I think we should move on to next speaker. Okay. Okay, thank you for the speaker.
Thank you.
Next speaker is Dr. Swagat Mishra. Are you there?
Hello.
Hi.
Hi, good morning.
Could you start sharing your screen?
Sure.
So you have 15 minutes, and I will let you know when 3 minutes are left. Okay?
Sure. Great.
And for just before we start, for the listeners, if you have any question, please leave in the message chatting box. Okay, I'll take a second to do that. Okay, so second speaker is Dr. Swagat Mishra, and he will talk about curing inflationary degeneracies using reheating predictions and relic gravitational waves. So please start.
Thank you. So today I'm going to talk about this work which is in progress, and I'm only going to talk about the first part of the work which has been already published. And this is the work in collaboration with Professor Sahni from my institute at IUCA and Professor Starobinsky from Landau Institute in Moscow. The paper got published last month, and you may have a look at it if you're interested later. I've given the archive and the journal reference here. So, vast amount of progress has been made in cosmology over the past 30 or to 40 years, and now we have our standard model in cosmology in the form of a flat lambda-CDM. However, the lambda-CDM is based on several assumptions as initial conditions, including homogeneity, isotropy, spatial flatness, as well as existence of initial fluctuations. Cosmic inflation has emerged as the leading paradigm of the very early universe, which explains these initial conditions for the standard hot Big Bang cosmology very appropriately. And inflation also has received spectacular observational confirmation so far. We are still yet to see the gravitational waves though. In the single field canonical minimally coupled inflationary model, we usually achieve inflation by having some kind of a potential where you have a regime where inflation happens and then inflation ends and universe reheats. That's the standard picture. And inflation would happen as long as this first Laurel parameter epsilon h, which is like a ratio between the kinetic energy and the potential energy, that should be smaller than 1. So as long as the field is rolling slowly, you achieve inflation in the standard paradigm. In the slow roll regime, which is a natural attractor in most of the inflationary models, you have both the first slow roll parameter, which has to do with the speed of the field, as well as the second one, which has to do with the acceleration. Both of them are much smaller than 1. Okay. And under this slow roll assumption, the power spectrum of scalar fluctuations take a very simple form, which is given by the Hubble square divided by the first slow roll parameter. Similarly, the power spectrum of the tensor fluctuations is purely given by only the Hubble scale during inflation. And these slow roll predictions fit a kind of a power law in the power spectrum. So the scalar power spectrum has a amplitude at some pivot scale, which is usually used to be 0.05 megaparsec inverse, and it has a tilt. Similarly, the tensor power spectrum has an amplitude at the same pivot scale as well as a tilt. And the tilt of the scalar power spectrum is completely given in terms of the slow roll parameters, and the tilt is usually predicted to be small. So NS is pretty close to 1. Similarly, the tensor to scalar ratio, which is the amplitude of the tensor power spectrum to the scalar power spectrum, is also given in terms of the first slow roll parameter. Okay. So we're going to focus on in this talk on the tensor to scalar ratio R, as well as the scalar spectral index NS. Now, during inflation, these fluctuations are produced as subhorizon quantum fluctuations, which go outside the Hubble scale during inflation, and then they freeze outside the Hubble scale, and much later they enter the Hubble scale and form a structure in the universe. So, characterizing these power spectrums at the 2-point level boils down to two important quantities, R and NS, and we measure R and NS about 7 e-folds around the pivot scale by CMB observations. Okay. And what we know from observations already is that R is smaller than 10%. So R is smaller than 0.1. So the data somehow stays here. We have an upper bound on R, and we have both upper and lower bound on the NS. So NS is measured pretty well. This eliminates a lot of models which are convex, but it still allows for concave and asymptotically flat potentials. One of the potentials which fit very well is Starobinsky inflation, and the other two potentials which fit also very, very well are the alpha attractor T and E models, which I'm going to talk about. So this olive color line, vertical line, as well as this cyan color bluish line, they correspond to the T and E model of alpha attractors, which satisfy the observations. So from the upper bound on the tensor to scalar ratio, we know that concave asymptotically flat potentials are favored, and we have upper bound on the Hubble scale during inflation directly from the tensor to scalar ratio, and that is around 10 to the power 13 GeV. However, uh, there are parameter space in the R versus NS diagram where a lot of models, several models, could predict the same result. And these give rise to inflationary degeneracies, which is the topic of my talk today. So the inflationary paradigm often displays several types of degeneracies. So either the degeneracy might come because completely different models predict the same value of NS and R, or in the same model, there is an extra parameter, lambda, let's call it lambda. And as you vary this extra parameter, R and NS do not change. Okay, you get same R and NS for even though you vary the extra parameter. Okay. So this is the second type of degeneracy that I will talk in this talk. Hence, because of these degeneracies, CMB observations of the 2-point functions of inflationary fluctuations cannot probe the physics during inflation uniquely. So it would be nice if we can break these degeneracies in some way. So before I talk about breaking it, let me demonstrate what are some of the degeneracies. Okay. I'll demonstrate it for two models, the T model of alpha attractor and the E model of alpha attractor. So the T model of alpha attractor has a very simple potential, which is a tan hyperbolic to the power 2 into P, where this P could be 1, 2, 3, or any integer. And this has a very simple symmetric potential with two asymptotically flat wings and minimum for preheating. Okay. Now, what happens is if we take this lambda, which is sitting here, this is related to the alpha of alpha attractor. And if you take this lambda to be greater than 0.1, then the NS and R predictions converge into some kind of a trajectory which is independent of the P sitting here. So whether I take tan square or tan fourth or tan sixth, I'm going to get the same NS and R as long as lambda is greater than 0.1. So that's the degeneracy, which is shown in this diagram. So for small value of lambda, our NS for P equal to 1, 2, and 3 are different. But as we go beyond 0.1, the P sort of, the NS and R, NS predictions sort of converge for all three P values. The same also happens in the R predictions. Here the shaded regions, these gray regions, are the regions allowed by observation. So there is especially a degeneracy at the place where we are making the observation. So since R and NS are independent of P here is an example of a degeneracies. Exactly similar degeneracy exists in the E model of alpha attractor, which is an exponential model. If you take lambda equal to 2 by root 6 and P equal to 1, you get the Starobinsky type potential. In the E model also, for lambda greater than 0.5, you get NS and R predictions which are independent of P. So you have a degeneracy there, which is also shown in a similar diagram here. So wherever observationally allowed regions are there, you have degeneracies there. Okay. Now I'll talk about breaking the degeneracies, and to break the degeneracies, there could be different ways to break it. But one of the ways is definitely to look at the reheating details after inflation. So CMB probes only a few e-folds of inflation around this blue star pivot scale. After inflation ends, the field oscillates and universe reheats, and the reheating history is not known at present, and it could be different for different models. So depending on that, it will be interesting. So reheating has several advantages. To consider reheating has several advantages in inflation. It's an important epoch, of course, because we go from inflation to the hot Big Bang phase through a period of reheating. But one of the main implications of reheating is that where is this pivot scale? how many E-folds before the end of inflation this pivot scale is, that is not known at present, and only the reheating details can fix it for a given model. Uh, the, so that is one thing. So which could be seen from this diagram, that if inflation ends here, how many E-folds before the end of inflation this booster could be is uncertain at present. The second implication is, which I'll talk now, is about breaking degeneracies of NS and R. Okay. And the third is, of course, the physics of reheating is extremely exciting. It's high energy and very interesting physics. But we'll talk about breaking the degeneracies. Okay. So after inflation is over, the scalar field sort of oscillates around the minimum. And if it has small couplings to other fields, like another scalar field, chi, or a fermionic field, psi, or it has self-couplings, then it will do particle productions. Okay, the production could happen perturbatively, or it could happen non-perturbatively. Non-perturbatively is extremely rich and interesting, but for this talk, I will only focus on perturbative reheating. In the perturbative reheating, as the scalar field oscillates, we can treat of this oscillating scalar field as a bunch of massive inflatons, which are almost at rest, and then they decay into very light scalars and spinors, whose mass is much smaller than the inflaton mass. And initially, it decays with some decay constant, but Hubble rate is higher, so the decay is very slow. But after a while, as Hubble rate falls, the decay rate becomes equal to the Hubble rate or greater. At that time, the universe, the inflaton decays completely and the universe reheats. Okay, in this perturbative picture. And the reheating temperature is typically of the order of 0.1 into root over of rate of decay into M Planck. And this value at maximum would be around 10 to the power 9 to 10 to the power 10 GeV. If this is too high, if this reheating temperature is too high, then the decay rate is too high, which means the couplings are too high, which will change the potential. So because of that, in perturbative reheating, you have a decay rate which is usually smaller, so you have a longer period of reheating and a lower temperature of reheating usually. And of course, there are non-perturbative reheating, which I will probably talk in a future work. So the advantage of perturbative reheating is the following, that if the inflaton is oscillating around 5 to the power 2p potential, at the end of inflation it's oscillating around some algebraic potential roughly, then depending on the value of p, the equation of state is known. The average equation of state is around p minus 1 by p plus 1. Okay. So if I know the minimum of the potential, the behavior of the potential around the minimum, I know the value of the equation of state during reheating. One advantage. The second thing is reheating is usually longer in the perturbative regime, because it's a not so efficient process. It's not very efficient. So we could have a matter-like equation of state during reheating. We could have radiation-like equation of state, or even stiffer equation of state, depending on what's the value. So if P is less than 2, so we have shallower than radiation, we call it shallow, otherwise we call it stiff. Okay. So reheating. So
yeah, 3 minutes.
Thanks. So reheating. Here we are not talking about the dynamics or the microphysics of reheating. Rather, we are talking about the kinematics of reheating. And the kinematics of reheating is usually described in terms of 3 parameters, which is the equation of state during reheating, the duration of reheating, as well as the temperature at the end of reheating. Okay, there's 3 parameters. And since we don't know these 3 parameters in general, we assume, so there's uncertainty in how many folds before the end of inflation the pivot scale left the horizon. So usually it's taken either 60 or it's taken the 50. So there's uncertainties because we do not know these reheating parameters. Now, if the post-inflationary equation of state is not equal to 1/3, then the duration of reheating is related to the number of E folds before which the pivot scale left through the equation of state during reheating. And the temperature of reheating is related to the number of E folds again. So if longer is the reheating, lower is the reheating temperature. Okay. And if the equation of state during reheating is 1/3, then it's difficult to define N reheating and reheating in this formalism. And we get a sharp prediction for the number of E folds and hence for NS and R. Okay. What we do is, given that there is a upper bound on the tensor to scalar ratio, This leads to an upper bound on the inflationary temperature, since in perturbative reheating, massive inflaton decays into lighter fields. So we could very conservatively and very generally put constraints on the reheating temperature to be in between 1 MeV and 10 to the power 16 GeV. So we take this very, very conservative bound, but this is good enough to break the degeneracies that I showed in these models. So this is where I plotted the number, the reheating duration and the reheating temperature as a function of NS for different models. And as you can see that even though NS lies for this green curve, for example, even though NS is, this green curve is within the allowed values of NS, but it is violating the reheating temperature constraint. So reheating becoming lower than Big Bang nucleosynthesis. So that's how it puts extra constraint. And if you put all this constraint, even though p equal to 1, p equal to 3, 2, p equal to 3, all went into the same NS and R, but once you put reheating constant, they're completely segregated. So p equal to 1 has an equation of state 0 and has NS in between these two values, and the number of e-folds where the pivot scale lives is around 50 to 55, not 50 to 60. And for equation of state 1/3, it's around 55. And for equation of state 1/2, it goes from 55 to 60. So that's how the degeneracies are completely segregated and completely broken in these models. In last 1 minute, I'll talk about also how gravitational waves can help in breaking these degeneracies. And the cosmological gravitational waves from inflation, these waves have a series of frequencies because inflation happened for quite long and lot many different modes left the Hubble scale. So we have a range of large range of frequencies where gravitational waves can exist. And these waves are also produced like the scalar fluctuations. So they are produced as quantum fluctuations, quantum tensor fluctuations, which freeze outside the horizon. They enter the universe at some point and then start oscillating and behave like gravitational waves. Okay, so depending on when they entered the Hubble radius in the universe, the frequency will be set today. So if you're observing in the detector today, their frequency will depend on when they made their Hubble entry. And the frequency is typically around 10 to the power minus 7 hertz if they entered around 1 GeV. If they entered earlier, they will have higher frequency. If they entered later, they will have lower frequency. Okay? At matter radiation equality, the frequency is around 10 to the power minus 17 hertz. But what is important is the Big Bang nucleosynthesis frequency. The temperature is around 1 MeV and the frequency is around 10 to the power minus 11 hertz. So reheating has to get over before this period. That's the minimal conservative constraint we have for sure. So then we can actually talk about the spectral energy density of gravitational waves, which in the radiative epoch has almost flat spectrum, while during reheating has a spectrum which has a tilt. Okay, it has a tilt which depends on the equation of state during reheating. In fact, the tilt is such that it has a primordial tilt, which is pretty low, pretty negligible, and the other tilt and the main tilt that we see at late times is because of the evolution of the universe, let's say during reheating. And depending on the equation of state, we could have a red tilt if it is shallow equation of state, and we could have a blue tilt if it is stiff equation of state. Okay, so here we plot for these green curves are for stiff equation of state during reheating. Here we have an absolutely low reheating, 1 MeV reheating temperature, and this black dotted line is for those waves which are entering, which have a reheating equation of state 1/3. The next, I show it for 100 GeV, and you can plot it for even higher and higher reheating temperature. But for perturbative reheating, it's usually low reheating temperature, so we show only low values here. In my last plot, I show you the behavior during reheating of gravitational waves. The behavior of gravitational waves, those entering during reheating, if the equation of state is stiff, or equation of state is radiation-like, or if it is shallow and matter-like. So you have a clearly distinct behavior of this spectral energy density, and that also helps in breaking the degeneracies. So to conclude, the epoch of reheating remains observationally unexplored and inaccessible at the present, in spite of a lot of theoretical development. and it has extremely rich high energy physics associated with it, but also it helps in breaking the inflationary degeneracies. And in this work, I just showed some small subsection of inflationary models where just perturbative reheating constraints can break degeneracies. And the breaking of degeneracies was achieved by only two simple conditions: that you have a period of reheating, however small it is, and you have reheating temperature constraint very conservatively in between 1 MeV and 10 to the power 16 G. And Rayleigh gravitational waves also provide a cleanest probe to study the epoch of reheating. I'll stop here. Thank you.
Another nice talk. It's time for questions. Any questions? All right, then let's thank our speaker again, and let's move on to the next speaker. Okay, so next speaker is Dr. Suruji Das. Are you there?
Yes, am I audible?
Yeah, I can hear you. Could you share your screen?
Yeah.
So you have 15 minutes, and I will let you know when 3 minutes are left, okay?
Okay, sure. So first of all, I'd like to thank the organizers for giving me the opportunity for this talk. So the title of my talk is Low-Scale Leptogenesis in Dark Matter in the Presence of Primordial Black Holes. So it is based on his recent work done with Devabrot Mohanto and Dr. Debashish Bora. So this is the plan of my talk. So I will start with the motivation behind their work. Then I will talk about some of the key aspects of primordial black holes. And then I will introduce the photogenic model, which is the setup we have used in our work. And then I will discuss about how primordial black holes can impact leptogenesis and dark matter in our model. And then I will discuss about another possibility of fermion dark matter in the same model. And then I will end with the summary and conclusion. So there has been this long-standing puzzle of baryon asymmetry in our universe, and in order to get the correct observed amount of matter, so in the early universe there should be a very tiny difference between this matter and antimatter. So this baryonic asymmetry is generally denoted in terms of this baryon to photon ratio, which is this current observed value from CMB and BBN. And also we have this dark matter problem in the universe, which has this current observed value of energy density around omega h square equal to 0.12. So now the standard model of particle physics, it fails to address these two problems. So there have been various studies beyond the standard model, like leptogenesis, WIMP, and so on. So these mechanisms are usually very high. One common aspect of these mechanisms is that they're very high energy phenomenon happening at around few seconds after the Big Bang, which is before the BBN era. So now there is no experimental evidence to suggest that our universe is radiation dominated prior to BBN. So motivated by this, we have considered a scenario where the universe can be dominated by primordial black holes in the very early universe, so which can be formed quite naturally in the through various mechanisms, like say some collapse of some inhomogeneities and so on. So now the mass of the black hole at the time of the formation at the temperature say T can be related to the mass enclosed in the particle horizon. Through this expression, so from here we can immediately get a lower bound on the black hole mass using the upper bound on the inflationary scale, which comes out to be around 0.1 gram. So now, as we know, there is a temperature related to a black hole, and also there one important quantity here is the initial PBH fraction. This is basically the ratio of the energy density of black hole to that of radiation at the time of the formation. So if beta is large enough, then the PBH may dominate the energy density of the universe. So once PBH formed, they lose mass to the Hawking radiation at a rate which is given by this equation. So here this A is the scale factor and this epsilon is the evaporation function, which contains information about the particles emitted by the black hole. And using this equation, we can find the time, or say the temperature at which the black holes have completely evaporated away. So this is basically inversely proportional to the initial PBH mass. That is, black holes with a smaller mass, they evaporate basically earlier, that is at a higher temperature. So we want our black hole to evaporate before the BBN such that it doesn't alter its successful predictions. So from this, we get an upper bound on the black hole mass around 10 to the power 8 grams. And if we want the black hole to have an direct impact on leptogenesis, then it should evaporate before the electric scalarian scale, which gives a tighter upper bound around 10 to the power 5 gram. So now, as I've mentioned, we have considered a specific particle physics model, which is the scotogenic model. So here the standard model is basically extended by 3 gas singlet right-handed neutrinos and then scalar doublet eta. So also an extra G2 symmetry is imposed under which these extra BSM particles are G2 odd. And this is the relevant Lagrangian of the leptonic sector, and this is the scalar potential, where this phi1 is the standard model Higgs. So as we'll see here in our analysis, the lambda 5 is an important parameter since it determines the Yukawas. So now, because of this G2 symmetry, there cannot be any neutrino mass at tree level. So, but there can be a neutrino mass at loop level, which is basically given by this expression, where this Y are the Yukawas and this L are the functions of the BSM particles which are present in the loop. So now this CPA symmetry in this model, if we ignore the flavor effects, can be written in this form, where again this F are the function of the mass of the BSM particles. So here I have shown the evolution of this co-moving B minus L asymmetry as a function of the scale factor. So here the variation of lambda 5 can be seen. So if lambda 5 is quite small, then the washout effects becomes important. So now, in order to study the effect of primordial black hole on the leptogenesis, we have solved a set of coupled Boltzmann equations for the co-moving number density of black hole for radiation, and also for the co-moving number density of N1 and the B minus L. And also here we solve for the temperature separately, because since entropy is not conserved here because of PBH evaporation. So here this N1 basically has 2 parts. One is the one is the usual thermal part, and one is the part which is produced from the black hole. So here the source term, which is basically the decay rate of black hole to the N1, can be approximately written through this expression, where this Li's are the polylogarithmic functions, and these ZBH are defined in terms of the black hole temperature. So now, depending on the black hole mass, it can evaporate at different times. So this naturally gives rise to 3 possible cases, basically. So now the black holes can evaporate before the scale of leptogenesis, or say during the leptogenesis scale, or after the leptogenesis scale. So here I have shown the evolution plots for the energy density, for the temperature, and for the number density, considering the before case where the black hole mass is taken to be 10 gram. And as you can see here, the black hole is evaporating around, say, log A equal to 7, which is much before the scale of leptogenesis, which is taken here to be 50 TeV. So here there are different regions, which I will be explaining in a moment. Again, this is a similar plot for the during case. So here the black hole mass is larger, around 7,000 grams. So here also you can see that in this temperature plot, there is a kink here. So this is basically related to the fact that entropy is not conserved here. And then we have, this is a similar plot for the after case. So here, naturally, as expected, the black hole mass is much higher again, so around 70,000 grams. Here I have shown the variation of the final baryon asymmetry as a function of the black hole mass. So here, since we are considering low scale leptogenesis, for most of the range of this PBH mass, the black hole is already evaporated by the time leptogenesis happens. So this is basically the before case. So here, basically, the N1 produced from the PBH, they basically act as an initial condition for the leptogenesis, and the final baryon asymmetry produces almost the same as that of the thermal case, which is shown by the dashed lines here. So, but as we keep on increasing the black hole mass, there is an entropy dilution, and the effect of PBH starts to appear, and we can see a dilution to give rise to the correct observed asymmetry. So in the top right plot, I have shown the similar behavior for 2 different leptogenesis scales. So in the bottom plots, some variation with the model parameters is shown. So now, as we know, if we increase the lambda 5, the leptogenesis in the thermal case is already very small. So the black hole mass required to dilute the asymmetry is further smaller, so which explains the pattern here. And similar pattern can be seen in the bottom right plot, where the variation is shown with the various values of light neutrino mass. So now coming to dark matter. So here the lightest scalar of the inner doublet can be a dark matter candidate. So it can be in thermal equilibrium in the early universe by virtue of its gas interactions. So now this typical WIMP phenomenon is modified in the presence of primordial black holes. So basically we can have 4 different cases depending on in which region the freeze out is happening. So in the first case, the freeze out happens at a very high temperature in which the universe is still dominated by radiation. So here we have the normal WIMP dynamics with subsequent dilution from PBH. In the second case, the PBH starts to dominate the energy density of the universe, but here still the radiation is behaving like a to the power minus 4. And in the third case, the PPH doesn't not only affects the Hubble, it also affects the standard model radiation, which now behaves as a to the power minus 3 by 2. And in the final region, the black holes have completely evaporated away, and we are again in a radiation-dominated universe. So we have the normal wave dynamics here with no further dilution from PPH. So now, since we want to study the effect of PPH on the wave dynamics, so we on the dark matter, so we basically consider the first three cases initially. So here. Here the total dark matter relay can be given, can have two contributions. One is from the dark matter produced from the black hole, and one is from the freeze-out mechanism with the appropriate dilution factor. So here, if we use the lower bound on the evaporation temperature, which is the BBN bound, we get a lower bound on the dark matter mass, which in this case is very trivially satisfied, because since we have a doublet dark matter, so the constraints from the direct search are quite higher than this value. And here we have shown the evolution of the co-moving number density of dark matter. So here we can easily see the dilution because of this PBH evaporation. So now we have considered the second part, which is the dark matter produced from PBH. So here we have used these analytical formulas and found the dark matter abundance. And here the plot is shown between for the dark matter relic as a function of the black hole mass for different values of dark matter mass. And in the right plot, the same plot is shown as a function of beta for different values of PBH mass. So from here, it can be seen that for most of the dark matter values, say around a few GeV to say around 10 to the power 8 GeV, this dark matter is overproduced. So this dark matter is overproduced unless this beta is quite small. So, and also the PBH mass, which can give rise to the correct dark matter relic, it falls outside the BBN bound. So next we consider another possibility in the same model, which is the leptogenesis from the N2 decay. So here, since the washout effects are quite strong, the leptogenesis scale is pushed higher. And here we consider the dark matter to be lighter, say around less than around 4 GeV, since we have just now seen that for dark matter with a higher mass, it is overproduced from the PBH. So here we consider a light dark matter, which is naturally a film dark matter candidate. So this dark matter can be produced from these different scattering processes, and also from the decay of eta. So here we have shown the variation of the baryon asymmetry as a function of the black hole mass. So here, in contrast to the earlier behavior, we see that in this in a small region of the PBH mass, there is an increase in this asymmetry. This is basically related to the fact that in this region, the right-handed neutrinos produced from PBH, they significantly affect the baryon asymmetry. But if the black hole mass is increased further, then this dilution effects starts dominating. And here we have shown the evolution of the co-moving number density of dark matter. So here we can see that the freezing is happening. So the freezing basically happens where when the number density of the parent particles here, which is basically the W plus in Z, so their number density, when they become Boltzmann suppressed, then this freezing occurs. So to summarize, so here we have shown the final parameter space in the M in beta plane, so along with the different bounds. So apart from the bounds from the on the black hole mass, which we have discussed earlier, there is this extra bound which is shown by the orange region, which basically where this overproduction of gravitational waves happen. So here we have shown the contours which give rise to the correct asymmetry for different values, for different leptogenesis scale. And this red dotted line, it basically is the separation between the PPS domination and the radiation domination. So here, as we can see, that this asymmetry is almost independent of this beta, unless beta is very small. So if beta is very small, then the effect of PPH basically starts to diminish. And in order to get the correct asymmetry, we need basically higher values of the PPH mass. And in the right plot, we have shown the contours which give the correct observed dark matter relic. So as we have seen earlier, that unless the PBH mass which can give rise to the correct relic, it basically falls outside the BBN bound. So one possibility is that we can have small values of beta, but then then if we have small values of beta, then this basically leptogenesis is unaffected. So here the only possibility we have is that this dark matter is freezes out after the PBH evaporation, such that this dark matter produced from PBH is enters into the thermal equilibrium. So, but one possibility could have been that if dark matter was lighter, then even for higher values of beta, we could have some allowed region, but this is ruled out from the direct dark matter bounds. Therefore, we consider this other case where we have considered a lighter dark matter. Now here, since we are in entoleptogenesis, the leptogenesis scale is pushed high. So the value of this asymmetric contour is basically shifted to the left because we require a lower value of PBH mass. And here we are in a case of mixed dark matter. That is, apart from this cold component, which is being which is given by this freezing component, we also have this potential warm component which is being produced from the PBH. So there is an upper bound on the fraction of this non-cold component with respect to the total component from various astrophysical and CMB observations. So here we have just used a conservative approach and imposed an upper bound of 10% on this extra warm component. So as you can see, this brown colored region, it gives more than 10% of this warm component. And so here we can see that this there is some region where it can give correct asymmetry as well as dark matter at the same time. So if we further decrease the dark matter mass, then this region gets shrink, and now this more region of this asymmetric contour gets allowed. So to conclude, so we have basically studied a leptogenesis in dark matter setup in a common setup in the presence of primordial black holes. So we have seen that these primordial black holes can itself lead to a source of leptogenesis, and it can also dilute the asymmetry. So we have seen that generally this dilation factor is more dominant. And in the first case of N1 leptogenesis in scalar dark matter, we have seen that it is not possible to satisfy this. It is not possible for the PBH to affect leptogenesis in dark matter at the same time. Unless this dark matter is very light, so we have considered the other case, which is where it is possible to have light dark matter, and it is possible to have some cogenesis with some dependence on the PBH parameters. So, and we have seen that this the constraint from the light dark matter, it has basically ruled out most of the otherwise allowed parameter space. And also this the range of these PBH masses we have used, it can have some observational consequences in form of gravitational waves in the future experiments. Thank you.
All right, thank you for the nice talk. It's time for questions. Any questions? All right, if no, let's thank our speaker again. All right, the last speaker this session is Dr. Malek Nejad, and she will tell us about Is Our Universe the Remnant of Chiral Anomaly? Oh, changing the title, sorry. Gauge fields in inflation and the origin of matter in the universe.
Oh, sorry, no, the title is the same, just the some another way to express that, yeah.
Okay. Yeah, we will hear, yeah. So please start. So you have 15 minutes, and I will let you know when 3 minutes are left, okay?
Perfect.
Yeah, please start.
Okay. Yeah, good day, everyone. Thanks a lot for joining, and thanks again for to the organizers for organizing this wonderful event. So I'm going to tell you about the possible contribution of gauge fields in physics of inflation, and the way that it may lead to a new framework that provide a deep connection between inflation, baryogenesis, and cold dark matter. In case that the inflaton field is an axion, it naturally couples to gauge field. And so the long story short, now the gauge field get generated by the axion. And therefore, this gauge field, which is active in physics of inflation, can actually source all the particles which are coupled to this gauge fields, like fermions, like the dark Higgs, and of course, gravitational waves. And interestingly, the source gravitational waves is chiral, blue tilted, and non-Gaussian. So it provides like an observable signature of this new framework. And then in principle, as a specific realization of this, this setup, one can assume that we embed the axion inflation in the left-right symmetric model beyond the standard model, which is basically just a standard model field content in which the now, in addition to only left-handed neutrinos, we also have right-handed neutrinos. And on the top of the SU2 left interaction, we also have the SU2 right interactions as well. And as you may guess, then this cold dark matter candidate that I'm going to talk about is basically one of the right-handed neutrinos. So we know that our universe is too simple, too symmetric at very large scales, and the leading paradigm to explain that unexpected symmetry is a period of exponential expansion shortly after the Big Bang, in which the scale of the universe increases by a factor of e to 6t. That's the so-called cosmic inflation. Although the exact particle physics of inflation is still unknown, but a scalar field slow rolling towards a true vacuum provides the simplest model for inflation. And the current puzzles of the standard model and cosmology, for which we need the physics beyond the standard model of particle physics, are the particle physics of inflation, the origin of the matter asymmetry, the origin of the neutrino mass, and the particle nature of dark matter. Also, from the cosmology side, we have these curious cosmological coincidences among parameters that shouldn't really be related. The first pair is eta baryons, the baryon asymmetry over the number of photons today, which is roughly equal to the curvature power spectrum in inflation, p zeta. And then the second pair is omega dark matter, which is equal to 5 omega baryons. And then finally, getting back to the standard model as a particle physics model, it also faces some conceptual issues like ad hoc parity violation, accidental B minus L global symmetry, and vacuum stability problem. Of course, based on who you talk to, they might find these conceptual issues or just not important. I personally think these are curious. So as yet, observations are in perfect agreement with inflation. The particle physics of inflation is still unknown. However, the standard model of inflation are based on a scalar field. So we assume that the inflaton is this scalar field beyond the standard model that we don't really know how it is connected to the rest of the standard model. And the primordial gravitational waves are sourceless. Therefore, they are just vacuum fluctuations, unpolarized, red tilted, nearly Gaussian. But what about gauge fields? You may say, oh, why gauge fields in inflation? Why not? Inflation happened at the highest energy scales observable to us. And gauge fields are all over the place, and they are the building blocks of the standard model and beyond. So what do they do in inflation? In case that gauge fields are not coupled to the inflaton or a field which is active in inflation, they will just get diluted like radiation. But in case that the inflaton is an axion, the gauge fields are naturally coupled to it. And therefore, the inflaton, which is now an axion, can source gauge fields in inflation. And that provides these gauge fields which are around. Just as a very quick remark, in case that you turn on a background for a U1 gauge field, it breaks the spatial isotropy. However, if it's a SU2 or a non-abelian gauge field, then it's possible for that to have a background which is perfectly isotropic and homogeneous. About the model building, the non-abelian gauge fields, and in particular SU2 gauge fields in inflation, has been introduced in gaugeflation, and then shortly after that, chromonatural. And inspired by them, several different models with SU2 gauge fields have been proposed and studied. This is a very incomplete list of models. But then you may ask, why so much attention to a model, to an idea so simple and basic? The reason is that we realize that SU2 axion inflation models have a very rich phenomenology. In particular, they lead to new mechanisms for generation of gravitational waves. All the Sakharov conditions are satisfied in inflation, and therefore they lead to a new framework for baryogenesis and leptogenesis in inflation. And also we have particle production in inflation by Schwinger effect and chiral anomaly because we have active gauge fields in inflation. My favorite realization is the minimal scenario of SU2 axion inflation, which is in agreement with the data. And this is basically an axion inflaton with a flat potential, which is coupled to this SU2 gauge field with a Chern-Simon interaction. And then, interestingly, this SU2 gauge field has a new tensorial degree of freedom on the top of the othermost, which is chiral. So if I decompose this mode in terms of its two different polarization states, then based on the sign of this parameter delta C, one of the polarization states will get enhanced. And delta C, its sign is basically given in terms of the sign of the axion field, if it's positive or negative. And then one mode will get experience some enhancement while the other mode is just decaying. Therefore, these particles are chiral. However, eventually, after horizon crossing, they all decay. But all the particles which are coupled to this gauge field will experience this particle production, which is happening around the horizon by this particle. And among different fields which can get coupled to this gauge field is the gravitational wave itself. So now, comparing to the standard scenario in which gravitational waves are sourceless, so the right-hand side is 0, now because we have this gauge field, they provide a source for gravitational waves. As a result, the final primordial gravitational wave is the vacuum solution, which is unpolarized and nearly Gaussian, and the part which is sourced by the gauge field. So now it's chiral and non-Gaussian. Why it's interesting? Because they are non-Gaussian, they can be probed with future CMB missions like LIGHTBIRD and CMBS4, and also they are blue tilted. So unlike the standard spectrum, they are blue tilted, and therefore they can also be probed by future laser interferometers. So this provides an observable signature for this setup. Now, how to connect this axion inflation and this idea to the standard model? As the simplest realization, I assume that now the particle physics is extended to the left-right symmetric model plus an axion field. And this SU2 gauge field that I discussed is basically the SU2 right in this beyond the standard model, which is coupled to the infraton. Left-right symmetric models has been introduced by Pati and Salam in the 80s, and since then this idea has been extensively, massively studied because of their interesting features. Here, the gauge group is extended with an SU2 right. And also instead of the hypercharge, we have to upgrade it to U1B minus L. The fermionic sector is also extended with free right-handed neutrinos. And we have an extended Higgs sector. Interestingly, this model for beyond the standard model can solve those conceptual issues that we discussed before. Now we get to the fermion production in this scenario. All the fermions which are only the fermions which are coupled to this gauge field that's directly coupled to the axion can get generated in inflation, while the other fermions, because they are coupled to gauge fields which are not active in inflation, they will just get diluted and they are not important. Those fermions who get generated are actually given by this key ingredient, which is the chiral anomaly of SU2 right in inflation, and it produces equal amounts of baryons and leptons in this setup. So baryon number is equal to lepton number by the end of inflation. However, B minus L standard model in the standard model sector is not zero, because part of this generated L is the right-handed neutrinos. And that's the key in this framework to actually work. Then after the freeze out of this right-handed neutrinos, we will have some final baryons, lepton standard model, and right-handed neutrinos, which eventually will get to their final values. The final baryon number generated in this mechanism is given by this relation, which is directly given by this scale of inflation, and also this alpha inflation, which is actually related to the efficiency of gauge field production in this mechanism. And we will have, if the lightest right-handed neutrino is feebly coupled to the rest of the standard model, then we have omega dark matter equal related to omega baryons with this, which gives us the mass of this N1 as the dark matter candidate to be around 1 GeV. Oops. So to conclude, gauge fields are expected to contribute in physics of inflation. As a compelling consequence, this setup can be a complete beyond the standard model that can solve these issues that we discussed before: the particle physics of inflation, the origin of the matter asymmetry, the origin of the neutrino mass, because the left-right symmetric model is a naturally has a seesaw mechanism inside it. And the particle nature of dark matter, because now the lightest right-handed neutrino is the dark matter candidate, and this framework provide a new mechanism for generation of right-handed neutrinos. Since this new framework provide a deep connection between inflation, baryogenesis, and dark matter, it can naturally explain these cosmological coincidences that we discussed before. And finally, it comes with a cosmological smoking gun on primordial gravitational waves. Thank you. Questions?
Yeah, thank you for the nice talk. Any questions?
Hi, can I ask a question?
Sure.
I was confused about your statement at the last slide that you said that it provides a new mechanism of generate of the origin of neutrino mass, but it's still the same, right? Because you have right-handed neutrino.
Oh,
SU2 right.
Yeah, I said, thanks for the question. Yeah, I said it leads to a new mechanism for production of right-handed neutrinos. But exactly, the mechanism for producing neutrino mass is by the seesaw mechanism, which is naturally entailed in the left-right symmetric model. So number 4 is new, like a new generation mechanism for right-handed neutrinos, but not for the neutrino mass. The neutrino mass is just like the standard one. Yes.
But number 4 is the particle nature of dark matter.
Yes, the particle nature is in this setup is the right-handed neutrino, but so the nature is right-handed neutrino. That's the same as the standard left-right symmetric models, but it provides a new mechanism for generation of them.
Yeah. Thank you.
Yeah, because within the standard left-right symmetric model, you also had different mechanism to generate them, but this one is different. So in the standard one, the source of CP violation is related to the neutrino sector or some other lepton violating interactions. In this setup, the CP violation is happening in inflation. So the source of CP violation is different, like a different physics.
Okay, thank you.
Thanks for the question.
Other questions?
Maybe
Right.
not. Maybe people are tired, they need a coffee.
All right, let's thank our speaker again. All the speaker this session. All right, so we will have break for 30 minutes and we will resume in 3:30. See you then.
Thanks a lot for having me. Bye.
Yeah, bye.